Today we are going to discuss the WKB approximation in quantum mechanics. Sometimes this is also called the semi-classical or phase integral approximation. This tries to approximate the Schrödinger wave function by a sinusoid whose frequency varies slowly. And usually the classical momentum and its integral with respect to position is an important parameter of the theory. Sometimes this is known as the phase integral. As it turns out, the wave function also has an amplitude which decreases very slowly with the inverse fourth of the classical momentum. Okay. Now this approximation was already known in the old days of electrodynamics when scientists tried to relate wave optics to geometrical optics. It is known that the word Eikonal, which comes from the word icon meaning picture, and which of course in history does have an important meaning as far as Istanbul is concerned, is such that in order to approximate the Maxwell waves with a classical picture icon, namely rays, which will form a picture, you have to perform a certain approximation, which turns out to be the same approximation as that used in the WKB quantum mechanical approach. Okay. Of course, if we look at the history of the electromagnetic theory, geometrical optics could be derived either from a wave picture of light, Huygens, or a particle picture of light, namely Newton and Fermat. In that sense, there was no wave-particle duality. Later on, when interference and diffraction was discovered, the wave picture began to gain in prominence, and furthermore, it turned out that when Maxwell was able to derive electromagnetic waves, and later on when Hertz was able to produce the electromagnetic waves in laboratory, the wave picture of light was firmly established. But in the meantime, eyeglasses, cameras were also working, which meant that somehow geometrical optics should find a place in the Maxwell theory. It turns out that the Eikonal approximation was used precisely for that purpose. Further discussion of that would probably be beyond the scope of today's lecture. Of course, this, namely unifying the wave picture of light with the rays, is of course an important unification. And as we know, in physics, we always try to unify different interactions and different fields in order to reach a simpler theory. Okay. Of course, when quantum mechanics began to be formulated, we knew that we could explain many physical phenomena in terms of essentially classical mechanics plus a number of ad hoc postulates, which at that time were quite unclear. Now, the important thing is that the old quantum theory could sometimes give very excellent results, such as the hydrogen spectrum, while in the same time give very nonsensical results, such as the angular momentum of the ground state of hydrogen in the old quantum theory is totally wrong. Of course, something else was needed. But in the meantime, there were a lot of successful instances of the old quantum theory, such as Landay's vector model, the photoelectric effect, even Compton scattering. Now, you may wonder why I am trying to stress this old quantum theory. Because as it turns out, the justification of old quantum theory actually is based on this WKB approximation, and we will use this as one of our examples. Okay. Now, the important connection between classical and quantum mechanics is the correspondence principle. In simple languages, it says that quantum mechanical results in the limit of the Planck constant going to zero, or the quantum number becoming large, goes over into classical mechanics. Actually, more can be said that every known formulation of quantum mechanics is based on a corresponding formulation of classical mechanics. In other words, much use, therefore, was made of advanced transformation theory of classical mechanics in deriving quantum mechanics. Now, the second important breakthrough, which really converted the classical and semi-classical old quantum theory to new quantum theory, was the discovery or the formulation of de Broglie waves. And immediately after the formulation of de Broglie waves, a very important principle was also discovered, the uncertainty principle. Now, why is the uncertainty principle important? Because it sets upon us a natural limit on our powers of observation. It also essentially is the solution to the wave-particle duality, because it compares a wave-like property with a particle-like property, and essentially says that the product of these two quantities is essentially a fundamental constant of nature, namely the Planck constant. Right. The Schrödinger wave function, therefore, was welcomed by scientists, because when Heisenberg, Born, and Jordan formulated the operator or algebraic theory of quantum mechanics, people were simply not used to it. Because in classical mechanics, people solved boundary value problems. In electromagnetic theory, likewise. So in other words, when Schrödinger was able to formulate the theory in terms of a boundary value problem, of course, it attracted attention, and quantum mechanics rapidly became known and began to be used very rapidly. Of course, we should remember that there are two very fundamental founding stones of quantum mechanics. One of them is, of course, the correspondence principle. The other one is the uncertainty principle. And if one understands these two principles, one can understand quantum mechanics. Now, essentially, if you wish, quantum mechanics is the physical optics of classical mechanics. Okay, now the classical trajectories which we have are like the rays of geometrical optics. While, of course, the wave function of quantum mechanics is like an electromagnetic wave, with one important difference, that physical observables are related to this wave function, but the wave function itself is usually not a physical observable itself. There are situations, of course, where that can be debated, but in general, like statistical mechanics, the quantities that enter into the equations of motion are related to physical observables, but they are not the physical observables themselves. Okay? Wave mechanics is right now called quantum mechanics because it was shown by Dirac that the wave and operator formalisms are equivalent, so that nowadays we just speak of the theory as quantum mechanics. Okay. Solving problems in the Schrödinger representation, of course, essentially meant again solving differential equations. And unfortunately, as soon as you begin solving problems, you have very few problems that can be solved analytically. So that in order to solve a more general class of problems, one approach, which is the perturbation approach, is to find an exactly soluble problem and then assume that your real problem has a small difference. The WKB is an alternate approximation scheme, and essentially it makes use of the fact that can we base the wave function in terms of an oscillatory solution or with slowly varying frequencies. Of course, the approximation actually was formulated by Wenzel, Kramers, Brillouin, and that's where the WKB comes from. Of course, Jeffreys independently formulated the mathematics of the theory, and this theory can explain a lot of things. As I mentioned previously, it can explain the semi-classical quantization method of the so-called older quantum theory. It can also explain tunneling in quantum mechanics, and those will be the two examples that we'll discuss during this lecture. Now let's begin to discuss the preliminaries of the WKB approximation. It is a semi-classical calculation in the sense that the wave function is assumed to be an exponential, where the exponential is an amplitude, consists of an amplitude and phase, which vary slowly. Of course, if you something very slowly in physics, we have to say what the other parameter is. The other parameter is, of course, the de Broglie wavelength. Okay, let's begin with the time-dependent Schrödinger equation. Let's do this in one dimension. Usually, the WKB approximation let's call approach if you want. Psi is the wave function depending on both position and time. And h is the Planck constant. H bar is, of course, the Planck constant divided by 2h. M is the mass. And V is the potential in the acting on the particle. Now, in order to solve this equation, we are going to first separate the variables, namely write as some u of x. Usually, phi of xt is known as the time dependent wave function, while u of x is known as time independent function, and it is e to the minus I e t over h line. And when the substitution is done, of course, we see that e to the minus I e t over h line factorizes out, and we get the time independent Schrödinger equation. And this is going to attract our attention. Of course, the WKB approximation is inspired by the following. If V is constant or piecewise constant, then of course, depending on whether V is greater than E or V is less than E, if the energy E is larger than V, the time-independent Schrödinger equation becomes is equal to 0, where Q squared is 2m E minus V over H line squared. Solutions to this equation can be sines, cosines, or imaginary exponentials. Namely, this should be sine qx, cosine qx, e to the plus or minus e qx, and physically we use this for standing waves, and we use that for traveling waves. All right. On the other hand, if the energy is less than V, of course, then of course we'll have d squared u by dx squared minus q squared u is equal to 0, and then the solution will be real exponentials. E to the plus or minus qx. All right. And actually, we'll be needing this for the tunneling phenomena. There is another point we should also stress. If we write the equation as in this form and compare this to the classical Hamiltonian, we see that we see that essentially this quantity here is the Hamiltonian, where P is H line times Q. All right. Up to now, we see that if the potential were constant, the solution of this problem is rather simple. Of course, we want there are two complications. One of them is, what if potential is not constant? And secondly, what happens when all of a sudden the quantity E minus V changes sign so that we go from one of these regimes to the other regimes? Now, at this point, we'll tackle those two issues one by one. Okay, let's now begin the WKB approximation, where, of course, the WKB approximation or approach is based on the fact that V of x is slowly varying. Well, what is the slowly varying? We mean that the variation in the phase is small compared to the slow compared to the de Broglie wavelength. In other x actually, the variation in x is small compared to the de Broglie wavelength. At this point, we should really move back to the time-dependent Schrödinger equation. Okay, and try to write is A of x e to the I s x t over the Planck constant. So that's what we'll try to do. Okay? Now, we can evaluate the derivatives as we need one more derivative. Unfortunately, here we have to do some writing. Okay, and then I'll need dψ by dt. dA by dt e to the I s over h line plus A e to the I s over h line times I over h line ds by dt. So this is just a simple process of taking derivatives. And now we'll just write the equation Okay, we'll just substitute this in the Schrödinger equation and take a good look at this blackboard, because I'll have to erase it in order to put that big equation onto the blackboard. Of course, e to the ix over h line will appear in every term in that equation, and it will cancel, so it will be I over h line. Okay. Okay. All of this is multiplied by e to the is over h line common factor plus like this. Now, what we'll do this, we'll multiply out and put this equation in descending powers of h line. Okay. Of course, we do have h line to the 0th power, which, as I told you before, will be somehow related to the classical problem. That equation will be, okay, order to the h line to the 0. Okay. Order h line to the 1 will be minus h line times 2 dA over dx ds over dx plus d squared s by dx squared times a plus dA by dt. Then order h line squared, which will be something like minus h line squared d squared a by dx squared. Now let's discuss each of these equations one by one. The h to the 0 order equation here is actually of interest in classical mechanics. Actually, it is called the Hamilton-Jacobi equation. However, discussing it is beyond the scope of this presentation. This will also tell me that if I separate, okay, variables in psi, which was as a product, that's how I separate it, remember, when I separate the time part. In this equation, I have to separate it as a sum because s is related to the logarithm, okay, of the wave function. Okay. Usually, we separate like this, S of xt is, this is of course for this Hamilton-Jacobi equation, W of x minus et, and then we get 1 over 2m times dw by dx squared plus the potential V of x is equal to the energy. Now, if you compare this to Hamiltonian, namely p squared over 2m plus v is equal to e, we see that really p of x is 2m e minus v of x, and actually it happens to be also dw by dx. Actually, this will give a complete classical description of the motion. Okay. Of course, we can integrate this equation and get that w of x is plus or minus the integral p of x times dx. This is going to play not only a vital role in classical mechanics, but also in quantum mechanics in this approximation. All right. Now, let's look at the next term, or the order h term. By the way, I'll have to now get myself some blackboard space. Okay. Okay. Okay, I can get rid of this one. That's okay. Let's look at this one. And for that, I'm going to, this will be the last term. I'll write this as 2 dA by dx, ds by dx, plus a times d squared s by dx squared. And momentarily, I will ignore this. With a justification for it coming later. I'll multiply this by an a, which happens to be an integrating factor. And this will give me d by dx of a squared ds by dx is equal to 0. We can get, by integrating this, the following. Okay. Okay, and if I remember that, remember what was S? I said S of xt was W of x minus E times t, so that ds by dx is actually dw by dx. It's nothing other than p of x. This magic p of x. We could also see it from right here. All right? So that we see that a squared times p of x is constant, and a of x is then k times P of x. Now, if you look at dA by dt multiplying by a dA by dt is 1/2 dA squared by dt, and if I just keep it, the amplitude, as independent of t, of course, this justifies dropping that term. So that we now have a wave function, satisfying this part. It is of the following form. Okay, so this, remember, will satisfy both the h to the 0 and h to the 1 equations. Okay, and together with this equation, px, of course px, I should have corrected the p of x is the square root of this from there, and so with this will be the basic WKB solution. Okay. All right. First of all, let's look at what is the error in this approximation. To derive the error in this approximation, we need to remember it was designed for a slowly varying potential. Notice that we can estimate the error by the order h squared term, and we can look at the following quantity for the error. Let's look at the second derivative, which, of course, h line squared times this is the error, and we can divide it by a to scale the error. Of course, for a, we do have a solution right here. It is k over the square root of px. So that we can calculate this as minus 2p d squared p by dx squared plus 3 times dp by dx squared divided by 4 p squared. Of course, we can also use this equation to relate the error in terms of Vx, which again is a matter of differentiating it. It will be as, it's also equal to minus Vx divided by 16. Now, let's make two observations here. One of which is that, notice that the errors involve derivatives of the potential divided by E minus V, which is essentially like P, so that, and then we see that slowly varying potential is required. However, there is another item here, namely we have E minus Vx here. So that if E minus Vx is going to be 0, then again this approximation is no longer valid. And we must complement this with something else. Now, let's look at what that something else is. Let's assume we have a potential like this. And here we have an energy E. Now, the WKB solution is going to be valid somewhere in here, inside the potential well, with a real exponential, with an imaginary exponential, and somewhere out there with a real exponential. However, it will not be valid at the turning point. Why do we call this turning point? Because classically, if the energy is less than the potential, the particle cannot come there, so that it has to turn back. We'll see that in quantum mechanics, it can tunnel itself through. However, somehow we must connect something like e to the iqx to e to the qx here, and e to the plus or minus qx. And the variation from a e to the iqx, which is a sine or cosine, to e to the qx, which is an exponential, is of course anything but slow variation. Which means that we have to devise another approximation near the turning points. Fortunately, there, of course, okay, let's look at this. Let's look at V of x. And let's assume that x is equal to x0 is a turning point. Then, of course, we can make a Taylor expansion. V of x is V of x0 turning point, which means E is V of x0 plus x minus x0 times the derivative of V at x equal to 0. So that if we call Z is equal to 2m times minus V prime x0 divided by h line squared to 3/2 in here, because here V prime is less than 0, and here, of course, V prime is, of course, greater than 0, because the function is decreasing there, it's increasing there. And with this potential, we end up, the Schrödinger equation then becomes d squared u by d z squared minus zu is equal to 0. This is, of course, at this point. We also have to look at this at this point. At that point, again, we use the same Taylor expansion trick. This time, v of x and now v prime is positive, so that we can now call z is equal to sorry, this I should have been x minus x1, where x1 is this one. I should have put this on 2m minus again v prime x1 divided by h line squared, again to the 1/3, 3/2, okay. That should be 1/3, sorry, because we have 2 powers of z down and 1 power of z up. And then, again, we get this equation. Now, fortunately, this equation, which happens to pop up on both sides of the turning point, has as an analytical solution, and we can return that to that analytical solution next time.